Hello. Am I audible?
Yes, sir.
Okay. So is my screen visible?
Yes, sir.
Okay. Okay. I think this is the place where I stopped in the last lecture, right? Applications of KSR.
Yes, sir.
Yeah. So we have three major applications. The first one is understanding the how the structure is related to the biological activity. So we cannot relate the structure directly to the biological activity with the help of molecular descriptors. We can make the relationship between the structure and the biological activity. So understanding how the structure is related to biological activity is the first major application of KSR. The second application is we can design compounds with improved biological activity, which means that we can use KSR successfully for the lead optimization technique. So once if you have a series of molecules having the same biological activity, so we can go for mathematical modeling called as QSAR, and with the help of QSAR modeling, we can do kind of lead optimization. I'll be giving some example in later slide. So the third major application of QSAR is we can predict the biological activity of the compound prior to the synthesis. So even before synthesizing the compound, with the help of QSAR model, we can predict what will be the biological activity of the new compound. So if the biological activity if it is high or expected, then we can go for synthesizing the compound. Otherwise we can drop it or we can trash it. So in summary, we can say that these are the three major applications of KSR. This is what where I stopped in the last lecture. So continuation of the previous lecture, there are three scientists who made contribution for the development of QSR. We can say that's how they made the foundation for the QSR. So the first person is called as Louis Hammett, and the second person is called as Free Wilson, and the third person is called as Hunch, right? So in modern QSR, the equation that we use as on today is called as Hunch equation. But Louis Hammett and Free Wilson, they have made big contribution for the development of QSR. So what I'm going to teach in this lecture is that what is the contribution made by Louis Hammett, what's the contribution made by Free Wilson and Hansch, how this QSAR field was developed. All the three are very big chemists. They developed the field called as QSAR. So this field, the first term QSAR, they published some paper in 1964 itself. Okay, so the method, what's called as a Free Wilson method and Hunch analysis. Both of the scientists, they work parallelly. They came up with two different ideas and published that. Both the ideas are like understanding how the structure is related to the biological activity. So this science is not new, right? So it's a long back story. They even started to publish papers related to QSAR 1964 itself. Okay. So let me explain what's the contribution made by Hammett, called as Hammett contribution. Okay, so if you take organic acids, we can classify the organic acids into strong acids or weak acid. Okay, so this classification is mainly based on whether the tendency of the molecule to donate its proton. Okay, so if this is the acid Ha, so if you put this acid in in aqueous solvent, so if it is dissociated into H plus A minus, so if you get the complete dissociation in the aqueous solvent, then we can say that this Ha is a very strong acid. On the other hand, if you have Ha and only partial amount of Ha is dissociated into H plus and A minus ion, okay, not complete 100%, then we can say that the Ha is not a strong acid. It's an example for weak acid. So depending upon whether the dissociation is going to be complete 100% or it's going to be partial, we can classify the organic acids into a strong organic acid or weak organic acids, right? um, so here, if you look at this image, so HA, as I said, that that's a kind of double-headed arrow here. There's a kind of equilibrium. So H plus, the HA acid is dissociated into H plus and A minus ion. So for this reaction, we can write the dissociation constant K. So this K is the dissociation constant, which is equal to the concentration of H plus ion times the concentration of A minus ion over the concentration of He. So using this formula, using this expression, we can calculate the dissociation constant of any given acid. Okay, so this is what I said. The strength of an acid, which depends on the tendency of the acid to donate its proton. Okay, so how easily this Ha can donate the H plus ion. Okay, that is going to determine the strength of the acid. Again, I repeat, if it is a very strong acid, it can very easily donate the H plus ion. If it is a weak acid, it can only partially donate its proton, not completely. So based on that, we can classify whether the acid is a strong acid or weak acid. Specifically, in case of organic acid, we can easily classify using this whether the organic acid is a strong acid or weak acid, right? So one point I just would like to add to this is, like, if you take any drug molecule, almost most of the drug molecules will be either as strong as either will be weak acids or weak base. You cannot find any molecule which is very strong acid or strong base. Okay. Okay, so this is the experiments what he did for relating how the structure is related to the activity. So he took series of organic acid. So this is the structure of benzoic acid. So this is the structure of benzoic acid. So what he did is he calculated what is the K, equilibrium constant for this benzoic acid. So if you put this benzoic acid in water, what will happen that this hydrogen, this proton H plus, will be cleaved, and you will get H C6H5COO minus plus H plus. Okay, so this proton will be released because this benzoic acid it's a weak acid. We cannot expect 100% of this dissociation. Only partial of the benzoic acid will be dissociated. This reaction will not be 100%, right? So what he did is very simple. He calculated what is the K value for this reaction. So in the previous slide, I have shown what's the formula for calculating the K value. So the calculated K value for benzoic acid is 6.2. So he termed it as a K0. Okay, which means that there is no substitution at any of the hydrogen atoms present in this phenyl ring. Okay, so K0 for this reaction, the calculated K0 value is equilibrium constant is 6.2. Okay, it's the first experiment what he did. So then what he did is he wanted to make some change in this position, at this position. So at this position, the benzoic acid is having a hydrogen atom. So we can say this hydrogen atom is at para position. Okay, so with respect to this functional group COOH, this hydrogen atom is present at para position of this molecule, of this ring system. So these two positions are called as ortho position. These two positions are called as meta position, and this is the para position. So he wanted to replace the hydrogen atom at para position with some other functional group. That is the experiment what he wanted to carry out. So for that, what he did is, first he removed the hydrogen atom and replaced that hydrogen with another organic functional group called as CH3CH2. So this molecule is called as ethane. Okay, CH3 is ethane. So this is ethyl. So what he did is he replaced the hydrogen at this position with ethyl group. Okay, so then he calculated what is the K value, equilibrium constant, after replacing the hydrogen at para position to CH3, CH2. So what he identified as the K value is 4.4. So if you look at the previous slide, the K value for the actual benzoic acid is 6.2. After replacing the hydrogen at para position with CH3, CH2, now the K value is 4.4. You can see that there's a kind of shift in the equilibrium. If you look at this, there is a kind of shift in the equilibrium. So the equilibrium, the length of the forward reaction and backward reactions are here illustrated same length, which means that the rate at which the forward reaction takes place, the same rate the reverse reaction is also taking place. We can say that that's a kind of equilibrium at that position. So but if you look at this reaction, that's a kind of shorten. This forward reaction is shortened, backward reaction is it's represented as very lengthy headed arrow, right? So two things we have to understand. That the first one is the K value is changing if we change the hydrogen at the para position. If we change the hydrogen at para position to CH3, CH2, the K value is now 4.4. It is no more 6.2. So he wanted to continue the experiment with some other functional group, changing with some other functional group at para position. So this time he has chosen another functional group, which is NO2. Okay. So first time at para position, hydrogen atom. Second case at the para position, it is CH3, CH2, CH3, and the third case, okay, he replaced with NO2, three different functional group. So after replacing this position with NO2, he calculated what's the K value. The K value drastically changed now. Okay, so from the K value is now 37.05. Okay, the value is now very larger comparing to the previous two cases, right? This is the experiment what he did. If even if you look at this, the shift of the arrow, you can see that now the forward reaction is a predominant, which means that more number of this acid will be present in its deprotonated state or ionized form. That is what we can say, right? So any conclusion can we make out of this three experiment? Am I audible? Am I audible?
Yes, sir.
Oh God. Yeah, my question is that can we make any conclusion out of whatever I have explained so far? Three kind of reaction he conducted, right? So can we make any kind of conclusion at this point?
Sir, dissociation depends on the incoming functional group or incoming group.
Dissociation depends on the incoming functional group. Okay, we will generalize, we will simplify. The dissociation constant depends on the functional group which is present at the para position. Am I right?
Yes, sir.
So what is the property of interest in this experiment? So in the previous lecture, we discussed about QSAR, we discussed about QSPR. I differentiated what is QSAR, QSPR, right? So if he wanted to develop a QSAR equation or QSPR equation, what is the property of his interest? So in this set of reaction, structure is related to what?
Release of H plus.
No.
Structure. Stability, sir.
In this series of reaction, he is trying to relate how the structure is related to function. Okay. He's trying to relate how the structure is related to molecular property. What is the molecular property of his interest? The answer is in the slide itself. So can we say that he is trying to relate how the structure is related to dissociation constant?
Yes, sir.
மேடம் நீங்க ரெஸ்பாண்ட் பண்றதை பார்த்தா கிளாஸ் எடுக்கிறதுக்கே எனக்கு இன்ட்ரெஸ்டே வர மாட்டேங்குது. Such a simple question. The answer is in the slide itself. Okay, so he got three different values while two different values while replacing with CH3, CH2, and NO2 group. Okay, so he wanted to check whether the same thing is happening for other series of organic compounds. So this time, can you tell what's the difference between this molecule and the previously shown molecule? Previously shown molecule is benzoic acid. The molecular formula is C6H5COOH. Can you tell what's the structural difference between the previously used series of molecule and this series of molecule?
There's an extra methyl group.
There's an extra
Methyl group.
methyl group, right? So I wanted to say that there is no extra methyl group here. The question is open for everyone, not for the person who answered. She told that there is an extra methyl group. I'm saying that there is no extra methyl group in this structure. There is no extra methyl group. Which functional group is present extra in this compound? Okay, you can answer. I'm just waiting for your answer. If I ask this question to even 11th standard student, definitely they can give very correct answer. Again, I show my slide. What is the structural difference between the previous series of compound and this series of compound? That's my question. Very simple question, very fundamental, basic question. No need to have extraordinary knowledge in organic chemistry. Even if you know what is organic chemistry, you can answer this question.
Carbon atom, sir.
Carbon atom. Who said?
Kavya.
Before giving the answer, you should think of do we have carbon here, or do we have carbon alone there?
CH2 group is attached. CH2.
We have CH2 group at that position. Okay, I do agree. So now my question is, can we call this CH2 group as methyl group? That is one girl answered.
So there's acetic acid attached to the benzene ring.
Okay, again I repeat my question. What is the structural difference between acetic acid is not already COOH is present in this compound? What is the structural difference between this compound maybe this is the correct example, this compound, benzoic acid, and this is called as a phenyl acetic acid. Okay, you should not answer, I think you can mute your microphone. Yeah. The acid group is already existing in the previous compound. Yeah, somebody can answer.
The nitro group.
Nitro group. I am taking this as example. Benzoic acid. Don't get confused. I'm comparing this structure with the benzoic acid structure. See, you have to compare this benzoic acid with this phenyl acetic acid. That's all. Somebody already answered it that there is a extra CH2 group.
Sir, functional
My
group is
question
not directly attached to the ring, sir.
Okay, different people having different answer. My question is, what is the name for this functional group? I
Methylene.
cannot simplify. Methylene, right? So it's not methyl. So the structural difference between the benzoic acid and phenylacetic acid is that this should not be called as a methyl group. You are going to appear for your project review this week, I think, right? So if anybody asks, don't tell that this is a methyl group. It's kind of absolutely wrong answer. CH2, it should be called as a methylene group, right? So here there is a addition of one methylene group. So methylene is CH2 group. Okay, so that's the structural difference between the previous one and this one. Since there's a kind of addition of methylene group, if you calculate the distance between this position and the hydrogen atom at this position, this series of molecules will be having larger distance comparing to the benzoic acid series. Do you agree? Because of the addition of one methylene group. Am I right? Again, I repeat, if you compare the structure of benzoic acid and phenylacetic acid, because of the addition of one extra CH2 group, that increases the distance between the hydrogen at the para position and the hydrogen which is attached to COOH. Am I right?
Yes, sir.
Yes, right. Okay. So now what he did is, for this series of acid, which is a phenyl acetic acid, he again wanted to calculate what is the dissociation constant, or K. So he calculated the K value for the phenyl acetic acid. So at para position, there's a hydrogen, no substitution at para position. It's having hydrogen atom. So here you can see that almost the forward reaction and backward reactions, they're going at the same rate. There's a kind of equilibrium, and the K naught value, calculated K naught value for this reaction is 5.2. Okay, K naught value is 5.2. Again, he wanted to do the same thing what he did for benzoic acid series. So he wanted to replace this hydrogen atom at the para position with CH3CH2 first, and then with NO2 group. So first he went for replacing the hydrogen at para position with CH3CH2. Again, he calculated what's the K value. So what happened for the K value? For the unsubstituted phenyl acetic acid, it is 5.2. So when he replaced the hydrogen at para position by CH3CH2, the K value, the calculated K value exponentially is 4.2. Is it increased or decreased?
Decrease, sir.
The value is now decreased, right? So then he went for replacing the hydrogen at para position by NO2 group. Then again he calculated what's the K value. Again he found that the K value is now 14.1 for replacement of the hydrogen at para position of phenylacetic acid. So is it increased or decreased comparing to unsubstitution of phenylacetic acid? Is this value increased or decreased comparing to the unsubstituted phenylacetic acid?
Increased.
The value is now increased, right? So what is your observation from all the three experiments? So he did 6 experiments. Okay, the first is he has chosen benzoic acid series. So he calculated the K value for benzoic acid. Then he replaced the hydrogen at para position with CH3CH2. He calculated the K value. Then he replaced that hydrogen at para position by NO2 group. He calculated the K value. So three experiments related to the benzoic acid. So second series of compound he took as a phenylacetic acid. Then he calculated what is the K value for phenylacetic acid as it is. Then he replaced the hydrogen at para position by CH3CH2. He calculated what is the K value. Then he replaced that hydrogen at para position with NO2 group and he calculated, right? So what is the observation here? What conclusion or what inference we can make out of this experiment, 6 experiments? Okay, if you want to answer this question, first we have to differentiate what is the difference between CH3CH2 and NO2 group, right? So what's the difference between all the three functional groups, hydrogen, CH3CH2 and NO2 group? So can you tell what's the difference between all the three functional groups? Okay, can you compare the property of CH3CH2 and NO2? How we can differentiate CH3CH2 functional group and NO2 functional group? What will be the impact of CH3CH2 functional group on any compound or on the phenyl ring? What will be the effect of NO2 functional group on the phenyl ring? So is my question understandable? Is my question understandable? Am I audible? Hmm? I know you people are kind of irritating me. Okay, I don't know whether I should continue or close the session. I'm not going to proceed unless until I have answer for this question. It's very basic fundamental question. What is the functional group difference between CH2, CH3, CH2 and NO2 group? If you don't know the answer, just Google search and come up with the answer, right? Then we can proceed. Okay, I give 5 minutes time for you, right? So you can refer some textbook or online resource. You have to tell me what is the functional group difference. Okay, major characteristic difference between CH3 CH2 group on phenyl ring and NO2 group on phenyl ring. That's all. That's my question. So once if you have answer, just come back, right? So we'll continue.
So CH3CH2 will donate H, while NO2 will accept proton.
Can you repeat your answer?
So CH3CH2 will donate the proton, while NO2 will accept the electrophile and it will accept the proton.
Proton, I don't know where comes proton. CH3 CH2 is donating the proton.
Yes, sir.
Donating proton. Okay. First I am hearing donating proton. Okay. NO2 group is it can accept proton.
Yes, sir.
Hmm?
Yes, sir.
Okay. So from where you referred this?
I didn't
Can
refer,
you
sir.
can you
No,
explain
sir.
how the CH3 CH2 can donate proton? Which proton of the CH3 CH2 will be donated?
Sir, while we increase or decrease the pH, the electron will hit and the hydrogen near carbon will be donated.
Mm-hmm.
And in NO2, if we change the pH, so if the O becomes O minus, it will accept hydrogen. I
Mm-hmm.
didn't refer anywhere, sir. I'm just telling my idea.
Okay, it is not right. I'm expecting some correct answer. Anybody else having any answer? What you have said is not right. Okay, it is not related to donating the proton or accepting the proton.
Okay, sir.
So if NO2 accept the proton, what will be the molecular structure of NO2? Will you say that NO2 will become NO2H?
No, sir. If we change the pH or a dissociation,
Yeah. Let me complete my answer. If we change the pH, right? So if you take NO2, you put the NO2 in some environment. Okay, whatever pH is the desired, right? So you just maintain that pH. At that pH, my question is that will this NO2 become NO2H?
no, sir.
Because you are saying that NO2 is it accept proton. For my knowledge, right? General chemistry, proton is H plus. If you say that some atom or molecule accept proton, it should go and add to that group, right? So my question is, do you say that NO2 can add H plus to it,
No,
whatever the
sir.
pH?
I'm telling like NO bond H may be formed.
NO?
O may form bond with H. I'm telling like this, not NO2H.
No. Okay. That's not right anyway. In any way that is not right. So any other answer?
Sir, sir, NO2 withdraws electrons, sir. CH3,
Okay.
CH2
So
donates
it is something related to electron. Okay, that's the first point. Absolutely right. So can you tell in terms of electronic property, what's the difference between CH3, CH2 and NO2 group?
sir. CH3, CH2 donates electrons, sir.
Okay, it is electron donating group and NO2 is
Electron withdrawing group, sir.
electron withdrawing group, right? So that's right. So CH3 CH2 is electron donating group and NO2 is electron withdrawing group. That's absolutely right. So if this is the characteristic, this is the difference between CH3 CH2 and NO2 in terms of its electronic property. So can you tell what conclusion we can bring into using these 6 experiments?
Sir, the compound which has NO2 will be more acidic, sir. It will easily give out the H plus.
Mm-hmm. Yeah, just go ahead.
And the
Okay.
electron donating group, that if it's present in the compound, uh, the ionization will not be easy, sir.
Okay. Who is answering?
Harivallavan, sir.
Okay, that is right. What he has said is right. So I just want to generalize, right? So what he said is absolutely right. So if we have the electron donating group at para position, or if you have electron withdrawing group at para position, definitely the value of the K value, the dissociation constant value gets changed. That is what he observed in his experiment. That is not only his observation is for two different types of series of organic acid. One is benzoic acid and another one is phenylacetic acid. For both the series he has observed the same pattern. Okay, while changing to electron donating group, the K value got decreased, and while replacing that hydrogen at para position with electron withdrawing group, the K value got increased. So what he did is he went for making a plot. So this plot on x-axis we have the K by K naught value for benzoic acid, the first series of organic compound he has taken for his experiment, and on the y-axis we have the log K by K naught value for phenyl acetic acid. Okay, so you know what is K, what is K naught? So can someone tell what is K and what is K naught? In all the 6 slides which I discussed in my so far, right? So we had the K value and K naught value. What is K and what is K naught? What's the difference between K and K naught? Is my question understandable? Am I audible? Am I audible?
Yes, sir.
No, it's kind of irritating me, right? So I just want to wind up the session. Okay, we will see sometime later. Okay.